This video shows calculations of a person on an inclined plane. The specific case is going to be someone skiing down a mountain that has kind of a strange shape. It's a smooth surface, and Robin is on this 29-degree slope. Starting from rest at the top, there's a coefficient of static friction between the skis and the snow of 0.23 I'm inventing, and a coefficient of kinetic friction while the person would be moving of 0.19. The hill has a length of 380 meters, and the person's mass is 56 kilograms. I'm going to calculate several things here. We're going to calculate the acceleration going down the slope, the time required to move a certain distance, and the speed or velocity at the bottom of the slope. So let's get started. I make a crude drawing, a sketch in this case, using the drawing tools in my version of PowerPoint, which are not outstanding, but I've got a skier, 56 kilograms, length of the slope 380 meters, claiming that it's a constant 29-degree slope. And then the coefficients of friction, mu is the coefficient, and sub s for static friction, k sub k for kinetic friction. And the person starts from rest, so their initial velocity is 0. What's the method we're going to use here? Here are the steps. First, I'm going to rotate the coordinate system. X will not be horizontal. Instead, X will be down the slope. The x-axis will be parallel to the slope of this mountain. We're going to calculate the force of static friction and see if the person moves at all. Is the force of gravity down the slope, that component, is that bigger than the force of static friction? Friction opposes motion, so the static friction will be directed up the slope. Will the person move? And yes, a little preview. So calculate the force of kinetic friction, and there's a difference between the kinetic and static because the coefficients have different values. Use Newton's second law to calculate the acceleration, calculate the time to move 380 meters, and calculate the velocity at the bottom, and then put this into something that students in the United States can relate to a little bit more. We're going from meters per second to miles per hour. Okay, hang in there with this kind of fuller screen. So the x-axis is along the slope of the mountain here. Let's first calculate the force of static friction. So the force of friction is equal to the coefficient times the normal force. Coefficient times the normal force. So come down to my drawing here. So the person's center mass would be up at the top of this right triangle. mg is a vector that goes straight down towards the center of the Earth, but it's not useful for calculating, not directly useful for calculating the normal force of friction. I have to use a normal force, and we'll get into the sines and cosines, but 29 degrees is the angle up at the top. The adjacent side here, so we'll be using cosine to calculate the component of the person's weight. Give us mg, the normal force. The person's component of weight pushes into the plane pushes back this way, creating a normal force that then we use in our model of calculating friction. For the component of gravity down the plane, we're now on the opposite side to this 29-degree angle, so we'll be using sine of 29 degrees to produce this number, the component of the weight down the plane. If you think about this, if the angle was 0, if the skier is on a horizontal surface, what component of gravity would be along the horizontal plane? It would be 0. And the angle would be 0 degrees. The sine of 0 degrees is 0. So I think we're making sense here. So let's go over to our equations. So the static friction is the coefficient of friction times its normal force. We're going to get the normal force by taking the component of the weight, component of mg, that's found by using cosine of 29 degrees. Cosine gives us the adjacent side to the angle. So putting in the numbers, you should pause here and pull out your calculator and verify I did this correctly. I've rounded off cosine of 29 degrees for this presentation, but when I actually did the calculators, I didn't bother rounding off the cosine number. I just let that stay on the display of the calculator, multiply 9.81, 60.23, and I got 118.4. And again, you're responsible for assigning the direction for the frictional force. Frictional force opposes motion. The skier is tending to move down the plane, so the frictional force is up the plane. And then for the component of the weight that's going down the plane, 60 kilograms, 9.81, sine of 29 degrees, this would be 285.4 newtons. Again, I keep one extra digit. The final answers, I'm going to usually round off to 3 significant figures, but intermediate answers I write down on paper, I would keep an extra digit, so 285.4 newtons. This component of the weight down the plane is larger than the frictional force up the plane. Static friction is not able to keep this skier from moving. So let's go ahead and move into that calculation. Let's find the force of kinetic friction now and the acceleration. Once you now know that the person is moving, you can no longer use the number for the static friction force. The coefficient changes. The mechanism of friction is different when a person is moving as opposed to stationary on a surface. So slightly different. We have a different coefficient, 0.19 instead of the previous number. And we get I'm sorry here. This should be F sub k. F sub k. I'll try to blot that out. The kinetic friction is now 97.8 newtons up the plane. And it's typical that the kinetic friction is smaller than the static friction. The force of kinetic friction is smaller than the force of static friction. So this is kinetic friction, 97.8 newtons up the plane. We have the same number for the component of gravity. The person's on this smooth slope at 29 degrees, so when they're moving, their component of gravity, their weight down the plane does not change. So we only had to change the friction number. Again, we use a net force calculation, and we find 285.4 newtons down the plane. Down the plane is my positive choice of direction. The force of friction is up the plane, so that's a negative number. And you can again pause and calculate the acceleration. I came up with 3.127 meters per second squared, keeping an extra digit for future calculations. But I asked my students to round off to 3 significant figures when they did homework problems. So 3.13 meters per second squared. Next, we want to find how much time to get to the bottom. Well, the skier starts at the top. I wanted to put the skier on the slope here, but from the point of the skier down to the bottom is 380 meters. And we know the acceleration. We don't know yet the speed at the bottom, the velocity at the bottom. So in the kinematic equations, I pick what I call the third kinematic equation. It does not have the final velocity as a parameter, as a variable here. We know how far the person's going to go. Their final position is 380 meters away from their starting position. They started from rest, so Vx naught is 0. And then 0.5, we calculated the acceleration on the previous slide, and then t squared. Again, pause the video, pull out your calculator. I came up with 243.04 as t squared. Taking the square root of both sides, 15.59 seconds or 15.6 seconds would be the time for the skier to move down 380 meters. What about the velocity at the bottom? Again, we know the acceleration number all along this slope. It's a level, I should say smooth slope. So we're assuming constant acceleration. We need that for the kinematic equation. So constant acceleration. So the velocity at the bottom equals the velocity at the top where we started, and then the acceleration multiplied by the time of the motion. The starting velocity is 0. The person was at rest. The acceleration number, we know the time. We just work that out to go down the slope. So I'm getting 48.8 meters per second, 48.8 meters per second. I don't have a lot of context that tells me much about 48.8 meters per second, a meters per second number, so let's convert it to miles per hour. So multiply by this conversion factor. 1 mile per hour is 0.447 meters per second. I got 109 miles per hour, which it's reasonable for a physics problem, but it's not reasonable to try this on your own, to go straight downhill without swishing back and forth to control your speed. So don't try this. Don't go straight down a mountain when you're skiing. Other question for you. This was a particular person. What if we use a different person with a different mass? Would we get a different number for the time or the acceleration or the velocity at the bottom? The answer is no, because the person's mass appears in every term in this Newton's second law. The net force, the component of weight down the plane, the friction involves using the person's mass to get the normal force, and then mass times acceleration here. So the mass cancels. I chose to use the mass just to so I could put this question at the end of the video, but you'll get the result, same result for anybody, a child, an adult, as long as everybody goes straight downhill and everybody has the same skis with the same coefficient of friction. If you want to see more of my physics and astronomy and miscellaneous topics YouTube videos, I have them listed at my website, gpclements.com. They're grouped by topic that you can fairly easily navigate. It's a very simple website, not fancy at all. Everything's free. You can't resell it. The videos, you're not going to give me your name or any information about yourself, not your email address. And my website does not put cookies on your computer. So hope you gain some physics knowledge from working through these sample problem videos, and ask your instructor if you have questions.